Welcome to This Explainer. Today, we're diving into the absolute marvel of engineering that keeps us breathing and, well, conscious miles above the Earth. It's this invisible lifeline that we completely take for granted when we settle into our seats for a flight. But honestly, the hardware and the science behind it are absolutely fascinating. I mean, really think about it. Why don't we just pass out at 30,000 feet? The upper atmosphere is a completely hostile environment for human biology. It poses this invisible yet incredibly deadly threat to us. So to survive up there, engineers had to devise some truly brilliant workarounds to trick our bodies into thinking we're still sitting safely on the ground. Here's our flight path for today. 1. The threat of hypoxia. 2. Storing aviation oxygen. 3. Continuous flow systems. 4. Demand flow regulators. And 5. Crucial oxygen safety. Section 1. The threat of hypoxia. Understanding the danger. Let's start by looking at the baseline of what we're breathing right now. Our atmosphere is roughly 78% nitrogen, 21% oxygen, and about 1% other gases. Now, you might assume that as we fly higher, the oxygen just kind of disappears and those percentages change. But actually, no. The real issue at high altitudes isn't the percentage of oxygen in the air at all. It's something else entirely. The real danger here is atmospheric pressure. Down at sea level, oxygen pressure is at 3.08 psi. But as you climb up to 40,000 feet, that pressure absolutely plummets to just 0.57 psi. Because of this massive drop, there just isn't enough force to push that 21% oxygen through your lungs and into your bloodstream. And that creates a sluggish, super dangerous condition in your mind and body known as hypoxia. Section 2. Storing aviation oxygen. 4 brilliant methods. So to prevent hypoxia, aircraft either have to heavily pressurize the entire cabin, which is what the big commercial transports do, or they have to bring their own tightly packed oxygen supply. Aviation engineers have come up with 4 distinct, really clever methods to store and generate this vital gas on board. We've got gaseous oxygen, liquid oxygen, chemical generators, and onboard oxygen generating systems. First up, let's look at gaseous oxygen storage. You've probably seen these iconic high-pressure green cylinders. They are specifically marked for aviators breathing oxygen. And the absolute most crucial engineering rule here, the water content inside these cylinders has to be practically zero. We're talking no more than 0.02 milliliters per liter of oxygen. If there's even a drop of water in there, the freezing temperatures at high altitudes will turn it into ice, and that would literally block the tiny passageways in the valves and regulators. Total disaster. Now contrast those tall green cylinders with this, liquid oxygen, or LOX for short. By dropping the temperature to a freezing negative 183 degrees Celsius, the oxygen turns into this pale blue transparent liquid. It's stored in these highly specialized double-walled spherical containers that basically act like giant heavy-duty thermoses. And the amazing thing about LOX, a really small amount of this liquid converts into a massive volume of breathable gas. It saves an incredible amount of space, which, as you can probably guess, is exactly why the military loves it. But what happens during an emergency on a regular pressurized commercial flight? Well, that's where chemical generators come in. These rely on something called a sodium chlorate candle. A spring-loaded firing pin basically smashes a cap, creates a spark, and ignites the chemical. But here's the catch. Once it starts, there is no stopping it. It cannot be extinguished. It'll just burn and give you a steady supply of oxygen for about 10 to 20 minutes, which is just enough time for the pilot to descend to a safe altitude. Oh, and real quick, there's also OBOGs, onboard oxygen generating systems, mostly used by the military. They ingeniously pass engine bleed air through molecular sieves to just separate out the oxygen right there in the sky. Section 3. Continuous flow systems. Emergency passenger net. Okay, so we have the oxygen safely stored. How do we actually deliver it? There are 2 main delivery solutions, and they're built for completely different purposes. On the left, we've got continuous flow systems. Think of this as a nonstop flow acting as an emergency safety net for passengers. On the right, demand flow systems, a highly efficient, mechanically triggered system designed specifically for the flight crew. Let's tackle the passenger side first. You have definitely seen these before. In an airliner, if the cabin suddenly depressurizes, these masks drop down automatically. Once you pull them to activate, oxygen flows continuously. But a continuous flow can be super wasteful, right? So engineers brilliantly added a rebreather bag attached to the mask. When you exhale, your breath actually still contains a lot of usable oxygen. That little bag captures your exhaled oxygen so you can inhale it right back in with your next breath. It's a remarkably simple way to conserve the aircraft's finite supply. Section 4. Demand Flow Regulators. Efficient Cruise Supply. For the flight crew, this whole setup gets a lot smarter. Let's walk through this ingenious mechanical step-by-step process. In a diluter demand regulator, oxygen only flows when the user actually wants it to. When the pilot inhales, it creates a slight negative pressure inside the regulator chamber. This physical pressure drop actually pulls a mechanical diaphragm over to the left. And as that diaphragm moves, it lifts a pressure-reducing valve right off its seat, allowing oxygen to rush into the mask. So literally, a simple human breath physically triggers the life-saving flow. But remember what we said earlier about pressure dropping the higher you go? At extreme altitudes, like 40,000 feet and above, a standard demand system just doesn't cut it. Even breathing 100% pure oxygen won't help if there's no atmospheric pressure to push it into your bloodstream. So for this, pilots use a pressure demand system. When that valve opens, it literally forces the oxygen into the lungs under pressure to guarantee blood saturation. It totally bypasses the problem of the thin air outside. Section 5. Crucial Oxygen Safety. Strict Protocols. Safety is obviously a massive deal here. You might have actually spotted this from the terminal window without even knowing what it was. On the outside fuselage of a lot of aircraft, there's this green blowout disc. It's connected directly to the oxygen system's pressure relief valve. If a pilot or a mechanic is doing their pre-flight walk-around and notices that the green disc is missing, well, that means the system's internal pressure exceeded safe limits and the relief valve blew open. Whatever caused that has to be investigated immediately before that plane can even think about taking off. And finally, we absolutely have to talk about the sheer volatility of pure oxygen. The maintenance manuals give this super intense warning. Pure oxygen drastically accelerates combustion. It will violently react with other substances. If pure oxygen mixes with basic petroleum products, like your everyday oils or greases used in routine maintenance, a literal explosion can happen. Mechanics have to make 100% sure that absolutely every single tool and piece of servicing equipment is completely clean of any petroleum residue before they even touch the oxygen system. So the next time you settle into your seat, listen to the safety briefing and look up at the compartment hiding those yellow masks. Think about the massive invisible pressure changes happening right outside your window. Think about the green cylinders, the mechanical diaphragms, and those chemical candles just standing by. Will you remember the incredible engineering fighting to keep you conscious? I really hope this explainer has given you a newfound appreciation for the invisible lifeline keeping us all safe up in the skies.